Yes, we are going to begin with the next chapter, which is Fourier series. So this chapter will be following from the book R.K. Jain and S.R.K. Iyengar, as it's mentioned over here, Advanced Engineering Mathematics, 4th edition. So this you will find otherwise in the library, but since you are not in the campus, so what you have to do is just look at the website. So we'll upload the questions for practice from there, directly from the book which you have to practice, and rest of the things you can follow notes and the tutorial sheets. Okay, so this is chapter number 9 actually in this particular book. So let me begin with Fourier series. So before directly giving you the definition of Fourier series, I would just have a general introduction about the subject, which will motivate you or which will give you a brief idea that why Fourier series is important and what is the main purpose for studying this kind of series. Okay, so I'll be recalling you few results which you have already done in last semester in the course Calculus Maths 1. So I'll give you an example of a series. So all of you are familiar with the word series. So we know what is tan inverse x. What is the series of tan inverse x? I'm going to write it down. X minus x cube by 3 plus x raised to power 5 by 5 minus x raised to power 7 by 7 and so on. So even if you do not remember this as a series, because we did remember some series, like for exponential function we know it has a Taylor series expansion, e raised to power x is 1 plus x square by 2 factorial and so on. We do know the series for sine x and cos x. So tan inverse x is also having a series. This is the power series, or you can say Taylor series expansion for tan inverse x, right? So if I'm going to put x equals to 1, what is going to happen? What will be you getting on the left hand side? Pi by 4. And on right hand side, what you will be getting? 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 and so on. So this is what is going to happen. So it's remarkable that on left hand side, you have a irrational number pi by 4, right? Everybody knows pi is irrational. But if you look at the right hand side, so on the right hand side we do have all rational numbers, right? So that's how the remarkable results about these infinite series is that if you infinitely many times add rational numbers, they can give you a irrational number, right? Because theoretically it is so. So on the right hand side, you keep on adding the terms, you will get more and more closer to the irrational number pi by 4. You will never be able to obtain exactly pi by 4, because we know that we are always doing the finitely many calculations. Howsoever, you can just increase the number of terms on the right hand side and increase the accuracy or precision. So this is possible because the right hand side series is convergent. Okay, so we all know that if you add two rational numbers, you will get a rational number. You will add three rational numbers, you will get a rational number. So the sum of rationals is going to be always a rational number, but sum of infinitely many rationals, as you can see, we are doing infinitely many, so it is going to be a irrational number. So let's generalize this result, or let's explore this result for some more kind of functions. So if adding rationals can give you an irrational number, so the question posed is for the functions, if you add continuous functions, can you get on the right hand side a discontinuous function? Means I'll just recall you that about the continuous function, we do have the results that if you have two functions, say f and g, which are continuous, right? Then what is f plus g? Is it continuous or not? Suppose their domains are same, so all those things are there. So yes, f plus g is definitely going to be continuous. We know that. I'll give you two function x square plus sine x. So x square is continuous, sine x is continuous. So x square plus sine x is definitely continuous. So this is something we know. Similarly, if I increase the number of functions, I'll say I'll give you 10 individual functions. Each one of them is continuous. You add them, the resultant is also going to be a continuous function. So on the similar lines, the way I explained you for rationals and irrational, on the similar lines, we do have the results that if you add finitely many continuous functions, right, the result is always going to be continuous. So now the question we are going to pose is what will happen if we add infinitely many continuous functions, right? So that is a question we are looking for. What is going to happen if we are going to add infinitely many continuous functions? So upon adding or upon doing their sum, the result can be continuous or the result can be discontinuous also. So uh, that is the, you can say, result because of infinitely many things. At infinite level, the things turn different, so we cannot generalize the results which are true for finite to infinite directly. So I'll be giving you example for this when we'll be particularly studying examples, but right now this is the basic idea, that this is a kind of series now we want to construct, in which we do have continuous functions, but we will keep on adding them to generate the discontinuous functions. This is not the aim, but this is, you can say, an application of that kind of series. So now let me recall you Taylor series. What was the condition of existence of Taylor series? If I'll give you a function f of x and I ask you to write its Taylor series or say Maclaurin series, so is it possible for every function? Are you able to write Taylor series for every possible function? Or was there some condition on fx which needs to be satisfied? Only then you can write the Taylor series expansion. Does anybody remember? Yeah, so if you remember the Taylor series expansion of a function about a point A, so f of A plus x minus A f dash A plus x minus A square f dash A by 2 factorial and so on. So we know that the terms keep on increasing, and in every term you are having a ordered derivatives, like nth term of this series is the nth order derivative of the function. So that means the condition was the function, this fx should be smooth function infinitely many times. This belongs to a class of C infinity functions. This is the notation, but actually it means that it should be infinitely many times differentiable. So it just does not only require continuity, but much more than continuity. It requires infinitely many times differentiability. So only for those functions you can write a Taylor series expansion. So now we will ask the question, what if our function is not even continuous, right? So like the above I explained you that we can write series for discontinuous also and represent them as the sum of continuous functions. So we want to do this even for the continuous functions, sorry, discontinuous functions. Like in Taylor series, what was the benefit? As you had e raised to power x 1 plus x square by 2 factorial and so on, and then you have the series for sine x and cosine x. So there we gave the reason that okay, we are able to do this and this is beneficial because transcendental function, the non-algebraic e raised to power x sine x cos x log x, these are our non-algebraic transcendental functions. We are able to write them in the sum of polynomials, because on the right hand side you're always going to get a polynomial if you truncate the term at finitely many terms. So because polynomials being nice functions, so that was the benefit. We can represent non-polynomial functions into polynomials. But now the new series which we are going to introduce, what that will do, that will help us to represent the function as a series of continuous functions, even though the function itself may not be continuous. Okay, so for that we are defining a series. Now what is that kind of series which is going to help us in that? So this is slowly we are bridging towards the definition of Fourier series. So we do have a series with which we can solve the purpose. So this series is known as, firstly, before giving you the definition of Fourier series, firstly we should know what is a trigonometric series. So the trigonometric series is basically a series of the form a naught plus a1 cos x b1 sin x plus a2 cos 2x b2 sin 2x plus and so on an cos nx bn sin nx and so on. So it's clear from here that this is going to be an infinite series. Again, whenever we are saying series, so we are always referring to infinite series, because finite series is just not contributing anything. Finite things do not produce anything new, right? So we are by default talking about infinite series. So it's a trigonometric series. Why it is a trigonometric series? Because you can see the terms. The terms appearing are either cosine terms or the sine terms. So all the terms are nothing but cosine of certain angle and sine of certain angles and their linear combinations. So these a naught, a1, a2, b1, b2, these are all going to be just constants, real numbers. And so in general, if I want to write it in more precise form, so a naught is just a constant term, and the rest of the terms I can combine in a general term, an cos nx plus bn sin nx, right? So this nx is the argument of the angle, right? So this is the general term. So any series of this kind, if you see a series written in this form, so that is a trigonometric series. Now we are particularly interested in trigonometric series of a particular kind, where these a naught, a and b and have some very specific definitions, right? So this a naught, a n, b n for all n, these are supposed to be constants. They are not going to be functions of x, they will be constants. But in Fourier series, the constants will be given some definition that from there they are coming, right? So the Fourier series was invented by Fourier himself, who was working on a problem in heat conduction. And the more examples are there in terms of the wave equation. So the wave equation and heat equation, they are explicitly part of your course. We will talk about them in detail when we will be proceeding in the chapter. At this step, it will be too advanced to talk about that. So then you will realize that okay, there is the application where Fourier series is used to solve the differential equations. So ultimately in this chapter also you will see we'll be using Fourier series to solve the differential equations, initial value problems and the boundary value problems and the partial differential equations. Till previous chapter, we were always dealing with ordinary differential equations. Even the Laplace transform was used to solve ordinary differential equations. But you will see in this chapter, this Fourier series is going to have applications in partial differential equations. So now what exactly is Fourier series? It is a trigonometric series where these a naught, a and bn are defined in a certain way. But before giving you that definition of Fourier series, I need to define periodic function. Although you might be clear with this already everybody should know what is the meaning of a periodic function. Yes. What is a periodic function? Which starts repeating itself after a certain period, right? So it's over its whole domain, its value keeps on repeating. So the formal definition, if you want to have for the periodic function, so I can write that a function f of x is said to be periodic if f of x plus p is f of x for some p real, and p is called the period of fx. So if there exists a real number such that f of x plus p is same as fx, so that means you just shift the domain from one point to another and you get the same values, and that number is fixed. So that number p is called a period and the function is said to be periodic, right? So that's very easy to understand, and we do know already examples of periodic functions. Yes, can you write examples in the chat box? Few examples of periodic functions. Sin x, cos x, right? So these are the first functions which come to our mind whenever we are talking about periodic functions. The trigonometric functions, sine and cosine, they are periodic. So we'll be using that definition, that example. So we know that sin x is a periodic function. Yes. What is the period of sin x? Sin x plus 2 pi. We know that this is same as sin x. And similarly, so this is the first example, this is the second example. So we know cosine x is also periodic. And what is the period of cosine x? Cos x plus 2 pi is cos x. Right. Apart from that, also we do have other functions also, but for this particular chapter, basically, as you have seen in the trigonometric series, we just need to you be dealing around with cosine and sine. So these two examples are sufficient. But I can give you a few more examples of periodic function, which is not in terms of this trigonometric function, right? So let me. I'll be drawing that function. I'll be making a graph of that function. Okay. So say this is the axis, x-axis, minus pi, pi. Say you have something like that. So from minus pi to pi, it's a straight line, right? Again, this. So you see, within the interval of minus pi to pi, if you look at the interval minus pi to pi, it's following a particular shape, and we know that is the line y is equal to x, because that is a passing through origin. And then after it crosses that interval pi, from pi to 3 pi, it again takes that value, right? So what is the difference? So you, this behavior repeats periodically, like this behavior repeats infinitely many times, because the domain of this function is a complete real line. And so on this side also it will be extended. So minus 3 pi to minus pi, so it is like this. So this is the function we have. So what is the period of this function? Say I have not defined it mathematically yet, but I have just shown you the graph. So you can still tell me what is the period of this? 2 pi, because the length of the interval over which it is attaining unique values is minus pi to pi. After that it starts repeating. So 2 pi is the length of the period, so that is 2 pi. And if you want to write mathematically, so mathematically this function can be defined like fx is equal to x for all x belonging to the interval minus pi to pi. And how to represent its periodicity is just by this formula, that within minus pi to pi it is defined by fx is equal to x, and after that interval what will happen, whatever will be points lying after outside that interval, for them you can compute values using this relationship, that f of x plus 2 pi is going to be same as f of x, right? So so what is the difference between the example number 1, 2 and 3? Example number 1 and 2 were continuous functions. They were periodic with period 2 pi, but they were continuous functions, right? So these two both are, we know. I don't even need to draw the graphs of these functions. Everybody knows sin x, cos x graph. We know they are continuous functions. But this third example, which I have just shown you. So what kind of function it is? Is it continuous? No? No continuity? No, it's not continuous. Then what it is? What will you give a name to this function? Jump kind discontinuity, yes. So it's a piecewise continuous function over the whole domain, right? It's piecewise continuous. As you can see, you can take any finite interval of the domain, and over that interval you will see the the kind of discontinuities which is appearing is only the jump discontinuity, and the jump is also finite in magnitude. As you can see, what is the jump size? Yeah, this value is actually pi. This value is actually minus pi, because this is a graph of y is equal to x, right? So value of x and y is same. So the jump size is 2 pi. So that's a finite jump. So it's a piecewise continuous function, right? So this gives you an example that even the discontinuous functions, the piecewise continuous functions can be there, which can be periodic. So we'll take up this kind of functions even more in this chapter, because we will be able to write them in the terms of Fourier series. So anyways, let's continue with the few more properties about the periodic function. So these are few remarks we have. So one thing which is something we already know, if P is the period, then 2P, 3P, 4P, these are also periods of the function f of x. If fx is a periodic function, because we know that fx plus 2 pi is fx, then fx plus 2 uh, n pi is also fx, right? So you give any multiple like 4 pi, that is also fx. You can take the example of sine x. Sine x plus 2 pi is sine x, which is same as sine x plus 8 pi. So 2 pi is any multiple is going to act as a period. So what to do if you want to define a unique period? So we choose the smallest one of them. So because if I ask you what is the period of sine x, everybody gives the same answer, 2 pi. So what you are giving as an answer is a unique answer, because that is the known as fundamental period or primitive period. Because as per the definition of period, the 4 pi, 8 pi, they are also periods, because the function's behavior repeats even after that length interval. But the 2 pi, the smallest such p, positive, right? Because negative bhi ho sakta hai. Even sign means you can go towards the other orientation. So the smallest such p positive is actually the called fundamental period, or also known as primitive period, right? Second remark is about constant function. Constant function is a kind of a trivial example of a periodic function, because for periodic function we want that the values start repeating themselves. So the constant function just have one value throughout the domain, right? So it's kind of by default the values are repeating immediately at the next point, but its period is not defined. Constant function is periodic, but fundamental period is not defined, because you are not able to find the smallest interval after which the values start repeating, right? Because the values start repeating immediately. You see this, if you look at the graph of constant function, this is something very trivial, right? So I'll ask you that give me an interval after which values start repeating. So you won't be able to find that smallest possible length of the interval. Whatever finite length interval you will be giving me, I can even shrink that interval to a smaller length, because it's continuously keeping the same constant value. So there is no smallest period. So fundamental period is not defined. So every real number is acting as a period, but fundamental period is not defined. You cannot find the smallest one of them. So that about constant function. Right. And then you have these relationships, that if period of fx is p, then what is period of fax? So this is p by a, and what is period of f x by a is a times p. So it's very easy to understand. So whatever will be the multiple of x coming, so the period gets divided by that. So we know that period of sine 3x is 2 pi by 3. So it does not need 2 pi to start repeating the values. After 2 pi by 3, it will start repeating the values because the x has been multiplied with 3, so the period gets divided with that number. So this is a general result, not only for trigonometric, this is for any periodic functions, that the period gets changed upon scalar multiplications. So that was about the periodic functions, and now I will be coming to the specific definition of Fourier series, because now we have defined a trigonometric series. So you might be knowing now why we are talking about these periods and all, because the trigonometric series contains a sine and cosine functions which happens to be periodic. So Fourier series, let me define what is this. So the first condition for writing Fourier series is a periodic function. If fx is a periodic function with period 2 pi defined on minus pi to pi, then Fourier series of fx is given by, let me complete the definition, then I'll be explaining the terms. Fourier series of fx is given by a naught by 2 plus summation n is equal to 1 to infinity an cos nx plus bn sin nx. So this a naught by 2 is just a convention, right? You can keep this as a naught also, but the point is actually there should be some constant. As I defined the trigonometric series above, I told you there is a constant term and then there are the multiples of sine and cosine and their further coefficients adding infinitely many times. So it's by 2 is just because now I'll be defining a naught, right? So that 2 has to be adjusted somewhere. Either you can adjust it here or you can adjust it in the formula of a naught. Let me first write what are these a naught, an, and bn. So far it is trigonometric series, but now with these particular values of a naught, an, and bn, we will be calling it a Fourier series. So a naught is 1 by pi minus pi to pi fx dx. An is 1 by pi minus pi to pi fx into cosine nx dx, and bn is 1 by pi minus pi to pi fx sine nx dx. So clearly a naught is just a constant. As you can see, the integral fx will be defined over the interval minus pi to pi. So when you will be substituting and the limits, upper and lower limits, it will get some constant value divided by pi. And an and bn, they are going to be functions of n, they are dependent on n, because for x you will be substituting the limits, upper and lower limits, but the answer of this integral is going to be in terms of n, because there are infinitely many, right? There is a1, there is a2, a3, a and so on, and similarly there is b1, b2, b3 and so on. So the answer of a and bn of solving this integral will be in terms of n, a function of n. So by these formulas, you will be computing the coefficients, substituting into your series. That series will be called the Fourier series. So this 2 I was talking about. If a naught by 2, in some books you will find that they just write a naught here. They do not write a naught by 2, but then they change the definition of a naught, because that 2 they have to adjust somewhere, right? So then the definition of a naught, what that will be? 2 by pi minus pi to pi f of x dx, because if you are changing there a naught by 2 with a naught, so there you have to multiply with 2 to balance the things. So it's just a convention, so we will be following this convention, a naught by 2, and where a naught is this, just to have a symmetry in the formulas and easy to remember the formulas, right? So let me just come back to the definition of this. So what is the condition required for a function to be written in terms of Fourier series? That it is a periodic function with period 2 pi. Because you see the series, right? If you look at the series here, what are these terms? What is the period of these infinitely many terms, right? Let me first ask you, what is the period of sine x plus sine 2x? Yes. Can anybody tell? What is the period of sine x plus sine 2x? It will be 2 pi, because you see sin x start repeating values after 2 pi, sin 2x although starts repeating value after pi, but the sum of them is going to be the largest period, right? अब आप इसमें अगर 2 pi करोगे, अगर आप इसमें sin of x plus 2 pi plus sin of 2x plus 2 pi करोगे, right? So this is going to be sin x and this is going to be sin 2x, but so that's why the period is 2 pi. But if you do sine x plus pi and sine 2x plus pi, you will not get the same function, because sine x plus pi is not going to be same as sine x, right? So it's clear that whenever you are adding two functions and one of them is having the larger period, so obviously the sum of the functions is going to have the larger period. दोनों की वैल्यूज 2 पाई के बाद ही रिपीट होंगी, सम की वैल्यूज ओवरऑल इंडिविजुअली दोनों का पीरियड अलग है, बट द सम इज गोइंग टू टेक अप द लार्जर पीरियड. So same is here. If you look at these terms, an cos nx plus bn sin nx, so cos x sin x will be, if you put n is equal to 1, the very first term is going to be cos x and sin x. They will be having period 2 pi, and the next term will be cos 2x sin 2x, so they will be having period pi, because I just explained to you, because 2x होगा तो period half हो जाएगा. And similarly the period start reducing with each and every term, but overall if you look at that as a function, so that is going to have a period of 2 pi. So that's why the condition is over the function fx, that function is periodic with period 2 pi, and this should be defined on the interval minus pi to pi. Now what does this mean? This means that the way I explained you the this example, that where is the fundamental definition of that function is given to you, that like you were defined, you were given the function definition, that function is defined for the period for the for the interval minus pi to pi. The same graph could be like the function is behaving fx is equal to x over 0 to 2 pi. So there will be always a smallest interval of length 2 pi over which function's definition is given to you, and for rest you have to replicate. So that's why some period is some interval they have to give. Most of the times that interval is minus pi to pi, but in few books or in few examples that can also be 0 to 2 pi. It is something we just need the function to be defined initially. The definition should be given to us for some period, for some interval of length 2 pi, right? So in our convention, what convention we are following, we'll be taking it from minus pi to pi, and otherwise you can take it 0 to 2 pi in some examples. We'll talk about those examples if they will be coming. It's the same logic which we used to give in while defining the argument of complex numbers, the principal argument, right? In some books you will say that the value of the theta lying between 0 to 2 pi is the principal argument, but in some books you will say the value of theta lying between minus pi to pi is a principal argument. So but we chose one convention. So same is here, we will be following this convention, that x lies from minus pi to pi. Only then these integrals make sense, the function is defined over there. Yes, so overall function is going to have whatever this periodic series, infinite series which you have written, this is going to represent functions with period 2 pi. So you got the condition for Fourier series, that we are going to talk about Fourier series for periodic functions. So for Taylor series, the condition was infinitely many times differentiable functions. For writing Fourier series, the condition is the function should be periodic and the period is 2 pi. Later on, we will generalize this to other cases. What if the period is not 2 pi, it is something else? We'll come to that later, but initially the definition is given like this, right? So I'll be just, tell you, don't, you can just ignore this one. We'll be following this definition. So this is the definition. So initially the kind of questions which we are going to do is simply you will be given a function and you need to find the Fourier series of that. And these formulas, these three formulas were given by Euler's, because this mathematician Euler was already working on the similar concept. So these formulas were derived already. So Euler's formula, this is just a name for them. Okay, let's just do an example. So it's the same example which I have shown you above, for which we did not know the expansion of that function. Okay, let me just write that. Find Fourier series of fx is equal to x minus pi to pi and fx plus 2 pi is fx. So you can see you are given the function defined over the interval minus pi to pi, and then after that it starts repeating the values. So directly we'll start evaluating the constants a naught, an and bn, and then we will be substituting them to get the series expansion. So what is the formula for a naught? So the formula for a naught is 1 by pi minus pi to pi fx dx. So this function satisfies our conditions, right? This is a function defined over the interval minus pi to pi, and it is periodic with period 2 pi. These were the two conditions required to be written as the Fourier series. So that's why we are finding that. What is a naught? So you just need to evaluate this. Yes, 1 by pi minus pi to pi x dx. So 1 by pi x square by 2 minus pi to pi, 1 by pi square by 2 minus pi square by 2, 0. So a naught is 0. Very easy, just a calculation. An. Now we'll be directly using the formula for an. Do not think that we will be evaluating individually a1, a2, a3, a4. We cannot do that. Directly we will be finding an, so as a function of n only. So the formula for an is 1 by pi minus pi to pi fx cos nx dx. So 1 by pi minus pi to pi, fx is x cosine nx dx, right? I'm telling you that this is going to be 0, right? So you can verify this calculation yourself. The integration is really not difficult. It's just two functions are given to you. You can use integration by parts. Do that integration, you'll get the final answer to be 0. It's really not tough. You can do that yourself. Okay, I'm telling you the answer to be 0. So what is happening here is, okay, I'll comment on this later. So you verify, you please verify this yourself. Yes, Uday.
मैम ये fx इक्वल टू x में तो कांस्टेंट फंक्शन मैम मतलब इसका पीरियड मैम 2 पाई होगा
नहीं, fx इक्वल्स टू x का पीरियड 2 पाई नहीं होता है बाय डिफॉल्ट, बट यू सी, यू रीड द स्टेटमेंट विच इज गिवन टू अस. ये कह रहे हैं कि माइनस पाई टू पाई में fx इक्वल्स टू x है. उस इंटरवल के बाहर आप अगर वैल्यूज कंप्यूट करना चाहते हो, सो दिस इज एन एडिशनल कंडीशन गिवन टू यू विद fx plus 2 pi is fx. So this is the same function which I shown you above graphically, कि विद इन एक इंटरवल उसकी वैल्यू. हाँ, इन जनरल अब आप पूछोगे y is equal to x पीरियोडिक है, ऑब्वियसली वो नहीं है. y is equal to x is not periodic, but when you are saying y is equal to x or fx equals to x, that means you are not giving me any additional information, so I'll assume that y is equal to x over the whole real line. So that's obviously not periodic, but here this is defined in this way, that y is equal to x for minus pi to pi, and after that it starts repeating. So then you will, if you draw the graph, it will come as exactly the same function जो हमने ऊपर draw किया है. Then you will see, okay, it is periodic. So it is given to us. So you will see these kind of examples, more examples coming in this chapter. that this is how the functions are going to be defined, periodic functions, because default जो sine cosine है उनके बारे में तो सबको पता है, how they are defined and how they are periodic. It is actually these kind of functions जिनके लिए हमें Fourier series expansion लिखना है, the
ओके
piecewise continuous functions.
एंड मैम हमने ए नॉट को अलग से क्यों निकाला था? हम सिग्मा n इक्वल टू 0 से नहीं कर सकते थे स्टार्ट?
नहीं नहीं, वो अलग है। ए एन जो है, ये ए एन है ना, आप इसके साथ कह रहे हो ना, ये एन 1 से स्टार्ट होता है, ए नॉट इज डिफरेंट। ए एन और बी एन जो है उनका समेशन इफ यू नोट डाउन, वो एन इज इक्वल टू 1 इंडेक्स से स्टार्ट होता है, सो ए नॉट इज नॉट कवर्ड इन दैट, वो अलग ही है।
ओके ओके
Yeah, so we are left with bn. Let me complete that. Bn is 1 by pi minus pi to pi f of x sine nx dx. Fx is x, because now I'm using, see, fx is equal to x, because you see the domain of my integral, I am integrating within the interval minus pi to pi, so there I know fx is equal to x, so I can use that. So if you will be solving this, so what you will be getting, uh, should I directly write the value? 2 by pi, sorry, I'm writing the values. I'm giving it a task to you to solve this integral. If it will not be solvable from you, then we can discuss this next time. But otherwise, it's easy. The integral is easy to solve. You can try this yourself, because as I've told you, the answer will be a function of n. X will be substituted with minus pi to pi. So it is 2 by n into minus 1 raised to power n plus 1. And while evaluating this, somewhere you will encounter cos n pi. What is the value of cos n pi? ये बहुत frequently यूज होने वाले formulas हैं. Sin n pi will be 0. Cos n pi is minus 1 raised to power n, because we know that cos pi, cos 3 pi, 5 pi वो negative 1 होते हैं, और जो cos 2 pi, 4 pi, they are plus 1. So remember these are going to be very frequently used. Cos of n pi is minus 1 raised to power n. Sin of n pi is 0. So we got the values of three formulas, a naught, a n, and b n, and you can see very well here that why a naught and a n are turning out to be 0. So if you remember a result from integration, that if you have something like this and minus a to a, and gx is odd function, so can you tell me the value of this integral? If gx is odd function, what is the integration from minus a to a? What is the value of this integral? It is 0. For odd function, if the limits are like minus a to a, this value is 0. So that is why for a naught and a n it is turning out to be 0, because the function, what is fx? Fx is x. We know that fx is equal to x is odd function, right? I just hope everybody is clear with the meaning of the definitions odd function and even function, but otherwise I'll again define them in the next class. And this, here the integrand was fx into cos nx. Cosine function is an even function, right? Cos of minus theta is same as cos of theta. So, but fx is odd. So odd multiplied with even will be odd, right? Odd into even function is going to be an odd function. So therefore, there also the value of integral is turning out to be 0, right? So even if you do not solve it completely, you simply give this logic that since the integrand is an odd function, you can directly write 0. That is why I have written directly 0 using this logic. But suppose you do not use this result and do your calculation, then also you will automatically get 0. So the choice is yours, but yes, we can use this concept wherever it is applicable. And what about even functions? So if you have minus a to a, f of gx dx, if it is even function, then it is 2 times 0 to a gx dx, if gx is happening to be an even function, right? So these results will be very frequently used throughout this chapter, because most of the integrals are of the type minus pi to pi, so they are always of the type minus a to a. So just by examining the integrand function, if it is odd or even, we can use these results and simplify our calculations. So while computation of this bn I have used this even, so it will be like 1 by pi into 2 times 0 to pi x sine nx dx, and then you can simplify this and this you will be getting as a final answer. So the final answer is Fourier series of given function is, so a नॉट बाई टू, सो ए नॉट तो जीरो ही आया है, सो पहली टर्म भी जीरो है, ए एन भी जीरो आए हैं, सो इट इज ओनली summation n is equal to 1 to infinity bn sin nx, because your series is a naught by 2 plus summation an cos nx plus bn sin nx, right? But since a naught and an are turning out to be 0, so that means it is only in terms of the sine function. So this is just this, and now you can substitute the value of bn. So bn is this. So uh, 2 by n summation n is equal to 1 to infinity 2 by n minus 1 raised to power n plus 1 into sine nx. So this, if you will be expanding this, you will be getting 2 sine x minus sine 2x by 2 plus sine 3x by 3 and so on. So this is the final answer, the Fourier series of the required function. So you see sine x, sine 2x, sine 3x all are continuous functions, but you infinitely many times adding them, the resultant is fx, where fx I have just shown you what was the graph of fx, that was a piecewise continuous function having jump discontinuities. So that was just the one example we did. We'll be doing more examples for finding Fourier series and even more general results for the same. So let me see if you have very quick doubts. Right? So these results will be very frequently used, even and odd functions concepts. So this is the final answer. Okay, so you try the integration part yourself, otherwise in next class I'll solve the same example. I'll show you how the calculation of integration is done. I'll also try to show this graphically how this is merging and giving you the same. I'll try to show you an animation for the same. Yes, Tanmay?
मैम जो आपने यहाँ पे बी एन साइन एक्स का निकाला है ऊपर इंटीग्रेशन, तो उसमें ये समझ नहीं आया माइनस वन रेज़ टू द पावर एन प्लस वन क्यों आया, माइनस वन रेज़ टू पावर एन नहीं आना चाहिए उधर।
नहीं, वो पूरा आप करोगे ना कैलकुलेशन तब आएगा। ये तो वो बीच में कहीं cos n पाई आएगा, माइनस वन रेज टू पावर n आएगा, बट कहीं पे कोई नेगेटिव साइन भी होगा, तो वो नेगेटिव इंटू माइनस वन रेज टू पावर n जो है माइनस वन रेज टू पावर n प्लस वन बन जाएगा। पूरा सॉल्व करोगे ना तभी आएगा
ओके
ये।
ओके
आई हैव
ओके।
स्किप्ड दैट कैलकुलेशन, या। Anyways, we are done with time, so I'll take your rest of the doubts in next time. Thank you.